Class number 7, daily summary. In this lesson, we introduce cryptography and we tackle substitution and bifid ciphers. Number 1, in this section and the next, we will discuss cryptography. These materials have been adapted with permission from James Hamblin. 2, how do we protect the security of the messages we send? This is a very important issue in the information age. Name some instances where we transmit information online that we hope is secure. So for example, every time you use your ATM, you hope that the interaction is secure and not interceptable. Same thing if you're looking up your medical records online. Same thing if you're sending a text message or a phone call placed from your cell phone, etc., etc. 3, it is largely impossible to prevent messages from being intercepted. Since we can't keep people from reading our messages, we should try to disguise them so the messages only make sense to the intended recipient. So anybody trying to grab our message is just going to get gobbledygook, but the person that we want to actually be able to read the message will be able to translate that gobbledygook into the actual message. So the process of disguising our messages is called encryption. Here's some vocabulary. Cryptography is the study of processes by which information is disguised so that unintended recipients cannot understand it. Encryption is the process of disguising the message. Decryption is the reverse process. A cipher, new vocabulary word, is a reversible rule for disguising a message. What does reversible mean in this context? Okay, so here's one example of a cipher. Take the message that you are trying to encrypt or encode and replace every letter with the letter A. So for example, if the word is mathematics, then you replace all 11 of those letters with A, and so it'll just say A, 11 of them. And so we have successfully encrypted our message into 11 A's, and then the person that wants to read our message will not have the ability to get back. It is this cipher where we replace every letter with the letter A is not reversible. We need a method for encrypting that is reversible, something that our intended recipient can undo. So translating everything to A's is not so great. Well, it's really good for encrypting, not so great for decrypting. 5, we want ciphers that are simple enough to use regularly but complex enough so that the messages cannot be easily decrypted by someone who does not know the rule. One of the simplest ciphers is called the Caesar cipher, named after Julius Caesar, 100 to 44 BCE, who used it to communicate with his generals. Here's how it works. Take the letters of your message and change them according to this rule. Each letter is replaced by the letter that is 3 places later in the alphabet. What happens when we get to the end of the alphabet? We simply wrap around back to the beginning. So for example, A gets replaced by the letter 3 places later, B, C, D. E gets replaced by the letter 3 places later, F, G, H. W becomes X, Y, Z. And then we get to the end of the alphabet here, X becomes Y, Z, and then we wrap around to A. Z wraps around and becomes A, B, C. We will typically omit spaces and other punctuation when we encode messages, since knowing the lengths of the words in our message could give the enemy a clue about the contents of our message. To help us do problems involving the Caesar cipher and other shift ciphers, where you just shift the alphabet a certain number of places, like 3 in this case, we will use the cutouts you made from page 3. So make sure you've got those cutouts handy. If you haven't cut them already, pause the video and go cut them. Let's move on to the next page. We're going to begin by encoding the message oatmeal using the Caesar cipher. So remember, every letter gets replaced by a letter that is 3 places later in the alphabet. So line up your 2 copies, your 2 pieces of paper there with the alphabets on them, so that O gets replaced by the letter 3 letters later. So let's see, that's LMNOPQR. So letter O becomes R, and then A becomes BCD. And pause the video and come back when you've got this thing encoded or encrypted. Okay, so my encryption is RDWPHDO. You'll notice that I've put a space after the 4th letter. That's pretty common to just group the letters in blocks of 4 or maybe 5. This makes it more readable for the intended recipient, but also doesn't give anybody stealing this message any information about word lengths. To decode a message from the Caesar cipher, we simply go backwards 3 steps in the alphabet. So here's a message that was encoded using the Caesar cipher. It starts EUH. Decode it and write your answer below. So it says here, we will often split the message into blocks of equal length to make the message more readable. The encoded phrase in this example was written out using blocks of length 4, even though it is a single word. So the spaces that we see here, it's not one word and then another word and then a really short word at the end. Turns out to just be one word, but that'll be obvious once we start decoding. So let's give this a shot. So to decode, we just do the opposite of how we encoded. So instead of going 3 steps forward in the alphabet, we go 3 steps backward. So line up your alphabet things in exactly the same way, but now I think you're going to read them in the opposite direction. So E, getting replaced by the letter 3 letters before, goes D, C, B. And then U, getting replaced by the letter 3 letters before, goes to T, S, R. So pause the video here and see if you can keep decoding this and then come back when you're done. Okay, so after decoding, we should have this. Again, it is not 3 words, turns out to just be 1 word, which is pretty obvious once you've got the decoded thing written out. So this is the word breakfast. Apparently I guess I was pretty hungry when I wrote this material here. 11, the Caesar cipher is an example of a substitution cipher, since each letter of the message is replaced by another letter according to a consistent rule. That is to say, every time you see the letter, let's come up here, every time you see the letter A, you replace it with a D. And here's another A, and here it is replaced with another D. So that is called a shift cipher. A substitution cipher. The cryptoquote puzzle in the newspaper is another example of a substitution cipher. You'll have a chance to play with one of those in the homework, and it says in the homework to not stress about it. It's supposed to be fun, so give it a shot, but don't worry about it if you can't get it. Substitution ciphers have a big weakness. The rule for substituting letters is always the same throughout the entire message. This makes encoding messages relatively easy, but messages can be deciphered if they are long enough. One method that can be used to break these ciphers is frequency analysis. According to the histogram below, what are the 3 most common letters in English? Okay, so you can see the letters down here, A through Z. And then over here, it's kind of hard to read, but I think these are percentages, how frequently each of these letters is used. So way up here at the top, you can see E is this tallest bar in the histogram. A little over 12% of the letters used in all the words in the English language are the letter E. Okay, so that's helpful. So it looks like E is the most common. Next most common maybe is right up here. So I guess that's a T. And then after that, looks like A comes next. E and then T and then A are the 3 most commonly used letters in the English language. And you can see very uncommonly used letters, or uncommonly, not often used letters. Looks like there's a J down there, poor Q, X not very often, and then Z barely even registers on the page. Using trial and error, it is possible to decode many messages by replacing the most common letters that appear in the message with E, A, or T, because we just saw those are the 3 most common letters in the English language, and looking for common words or prefixes or suffixes. So for example, the word the is really common. So if you happen to see a 3-letter word, you might just guess and get lucky that it is the word the. Let's see, so I mentioned you'll have a chance to try to crack a substitution cipher and an optional cryptoquote in the homework. The main problem with substitution ciphers is that the order of the letters does not change. More advanced ciphers can involve rearranging letters to try to avoid this problem. Here's one now. We now learned about the bifid cipher, which uses a device called the Polybius square. Let's fill in the alphabet in order in this grid by going across the rows. We're going to skip the letter J since there are only 25 spaces, but we have 26 letters. So A, B, C, D, E, and then we continue in the second row. F, G, H, I, but we're skipping the letter J because we've got to skip something. There's only 25 spaces here. So we skip J and make it a K. L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, and Z. If it happens that we really need a J for whatever reason, like there's J's in our messages, we can just replace the J's with the letter I and assume that our intended recipient is going to be smart enough from the context of the message to change them back to J's. Next page, we can also create a square based on a keyword of our choosing. We start by filling in the letters of the keyword across the rows, leaving out duplicates. Let's use the word confidential. Fill in the letters of the keyword confidential in the grid below, going across the rows but skipping any letter that you've already written. For example, we won't write the second N. Let's give this a shot. Okay, so spelling out confidential. C-O-N-F-I-D-E. Okay, and then as soon as we get to this N, we say, wait a second, we've already written the letter N before. It was right here. And we're not going to duplicate any letters in this square anyplace. So we skip the N. We go to the next letter, which is a T. Next letter after T is I, but we've already got an I here. So we're not going to write the I. We're not going to duplicate it anyway. And then A-L. Okay, and now 16, fill in the rest of the alphabet, again going across the rows and never duplicating a letter. So that is to say, we're just going to start over in the alphabet here with the letter A. So we're going to go A, B, C, D, E, etc., all the way to Z, but we're not going to repeat any letter that's already been written any place inside of our square. So normally I would start here with an A, but I say, wait a second, I've already written an A, so we're not starting there because we don't want to duplicate. So the next letter is a B, which we have not written anywhere. Next letter would be a C, but wait, we've already got a C up above. After that is a D, but wait, we've already got a D, and in fact, we've got an E as well, and an F. So the next letter in our alphabet is G. That's the first one that doesn't appear in our word. So we just carefully keep going. So G, H, I, we've already seen. J, we always skip. K, L, we've got. M, N, we've got. O, we've got. P, Q, R. S, T, we've already seen. U, V, W, X, Y, and Z. It is always a big relief to me when I get that Z in the last square, because if the Z didn't fit, or if the Z happened to appear in the second to last square, that means I made a mistake. Okay, here's the process to encode using a bifid cipher. We create a polybius square using a keyword. We just did that, and it's copied down here below. We look up each letter of our message and write the numbers with the row on top of the column. All right, let's do that here. 17. Let's do an example where we encode a short message, the word retreat. We're going to encode that. As we will see, the bifid cipher requires messages to have an even number of letters, but retreat has 7 letters. So we're just going to attach a dummy letter, dummy character to the end. So down here at the bottom of the page, you can see we've got this funny grid set up. We've got the word retreat written across the first row, and then we'll just attach a meaningless X at the end. It'll be clear soon enough why we needed to have an even number of letters in our message. Okay, so all we're going to do is we're going to look up the letters in the word retreat X inside of our square, and we're going to record the row and the column. So the first thing we see, highlighted here, is an R, and we find the R someplace in our square. It only appears once. It is in row number 4, column 3. And so we record those numbers in our chart. Row 4, column 3. Next up is the letter E, and we find it in our chart. It is row 2, column 2. Next up is the letter T. Find it in the chart. That's way up here. Row 2, column 3. Make sure you get your numbers in the right spot. If you put 3 and then 2, that's a problem. It's not going to work. Okay, you can look up R, but actually we've already seen R, and it's still in row 4, column 3. So that's easy. If you have duplicate letters, you can grab the info from before. E, oh, that's another duplicate, 2, 2. Okay, where is A? Oh, we see A right up here. That is in 2, 4. T we've already seen, that's still in 2, 3. And then finally X, which is down there, 5, 3. Okay, so we look up and we put the information row number on top of column number. So that's part B. So look up, write the numbers with the row on top of the column. Part C says group the numbers in pairs, reading across from left to right. So this is going to be kind of funky here, but I'm just going to circle these numbers in pairs. Now, it was row 4 and column 3. The 4 and the 3 were the things that were grouped together, and then a completely separate pair was 2 and 2. But we're going to group them in a different way, a way that maybe has no meaning in the scope of this message, which is kind of the idea because we're trying to take away the meaning of this message. So we're going to group in pairs going across. First pair was 4, 2, and then 2, 4, and now 2, 2, and 2, 5. And then we get to the next row, and we just keep going in pairs, 3, 2, 3, 3, 2, 4, 3, 3. Okay, and now we are going to take all of that information and look it back up in the table. And so the first thing that I circled in this now new meaningless pair is 4, 2. Fourth row, second column. I know that the 4 and the 2 were both row numbers originally, right? The 4 and the 2 both appeared in this thing that says row, but we're not going to read it that way. We're going to treat the first number in the pair as the row, second number is the column. First is the row, second is the column, first is the row, second is the column, and we're going to keep going, row and column. And we're just going to come up with a new gobbledygook message based on the new row and column. So row 4, column 2. Row 4, column 2. That's a Q. Oh, perfect. That has nothing to do with any of the letters in the word retreat. Next up is here, 2, 4. So 2 and 4, that's an A. Next up is 2, 2. So row 2, column 2, that's highlighted in green there. That's the E. Q, A, E. And then last one here in the top row is 2, 5. Row 2, column 5. Row 2, column 5. That's an L. And then we just keep on trucking in the next row. 3, 2. Third row, second column. Third row, second column. That's a G. 3, 3. Third row, third column. That's H. 2, 4. Second row, fourth column. That's an A. And then finally 3, 3. Third row, third column is an H. Okay, so our encoded or encrypted message is QAELGHAH. Hopefully it's clear now why we needed an even number of letters. If we didn't have this here, then when we went to go circle 2, it wouldn't have had a partner. So that's why we need an even number of letters in the message. Okay, so I think we got this. We grouped the numbers in pairs, reading across left to right, and we looked up the new pairs of numbers in the Polybius square, where the first number in the pair is the row, and the second number in the pair is the column. Okay, next page. Is bifid a substitution cipher? That is, does each letter always get encoded to the same letter? Well, let's take a look. The word retreat had plenty of duplicates, so I'm going to write the word retreat here just to see if it's a substitution cipher. We'll put our X at the end. Let's see. We've got an R here, which got mapped to the letter Q, and then we have another R here, which got mapped to the letter L. Hey, that is not a substitution cipher. We did not consistently map the letter R to any single letter, like in the Caesar cipher. E got mapped to A, but the other E got mapped to G. T got mapped to E, and the other T got mapped to A. So definitely not a substitution cipher, which makes this a much stronger cipher to use. So bifid is not a substitution cipher. 19, to decode a message, simply reverse this process. Look up each letter in the Polybius square, writing down the row, then the column, but write the numbers left to right. Then split the message in half and put the second half below the first half. Finally, decode the message by looking up each letter in the Polybius square. Let's give this a shot. Here's the encoded message. EXPT, etc. was encoded with the bifid cipher using a Polybius square based on the keyword Mississippi. Let's decode the message. Okay, so first we got to put the keyword here, Mississippi, M-I-S, but remember we don't duplicate, so we're not going to put another S. M-I-S-S-I, we're not putting that. S-S, not putting those. I, not putting those. P, not going to put the second P, not going to put the final I. And then we go with the rest of our alphabet here. A, B, C, D, E, F, G, H. Don't do I because we've already seen it in Mississippi. We never do J. H, I, J, K, L, M. Nope, already seen M. N, O, P we've seen. Q, R, S, plenty of those. T, U, V, W, X, Y, Z. And again, I breathe a sigh of relief on that Z. Okay, here we go. I'm going to copy our encoded message here. EXPT, N, G, F, G. And then finally a YD. Okay, so let's give this a shot. we are going to first look up the E. So looking for E, it is right here. It is in the second row, fourth column. So in the encoding direction, it was row and then column that way. But remember, we're going the other direction. And so we have to recognize that somebody encoded this message by looking at the 2 and 4 this way. Okay, so that was the E. I'm just going to pull check marks because it's pretty easy to get confused as to which letter we're on here. Okay, next letter is X. Okay, looking for the letter X, it's way here at the bottom. It is in row 5, column 3. Remember, write them horizontally, 5 and 3. X is now done. Next up is the letter P. Okay, P is way up here. That's a 1, 4. So we go 1, 4. And now P is done. And then we proceed along to T. So T is here. That's 4, 4. And again, we write it as a row, 4, 4, straight across. And that's the letter T. Checked off there. Let's do one more letter, and then we're going to change things up. N. Okay, looking for the letter N. That is here, 3, 5. 3, 5. Okay, and now I've kind of run out of letters over here, right? We're out of space. And so what that means is that we have reached exactly the halfway point of our encoded message. The whole thing here had 10 letters in it. We have just done the first 5. So you could keep going. You could just go out here with the next thing, right? We're looking for a G here. We can just put those 2 numbers there and keep going. But why don't we just save ourselves some time and recognize that, hey, at the end of the day, the other numbers had to come from this bottom row. And so we're just going to keep going, but we're going to now start putting numbers in the bottom row. So let's go. G is right there. That is a 3, 1. But now we're going to put that here, 3 and 1. And now G is done. Okay, next up is F. We can see the F is in 2, 5. Let's pick up the pace a little bit here, 2, 5. And now F is done. G we've done already. Let's find it again. It's still in 3, 1. So we put a 3 and a 1, and then we check off G. Looking for the letter Y. That's near the bottom right, 5, 4. And Y is done. And then finally D is 2, 3. And D is done. And now we say, okay, somebody kind of artificially had grouped the letters this way, but we're going to go back to the way that we know they were originally grouped, which was this way. And so now we're just going to be reading rows and columns as they were meant to be. And now we just look these things up in our square. So row 2, column 3, 2, 3, that is a D. Let's go a different color here. Okay, so that becomes D. 4, 1. Looking for row 4, column 1, that's an O. 5, 2 is a W. 3, 5 is an N. Okay, we're down. So go ahead and pause the video here and see if you can find the remaining decrypted version of this. And then come back when you're done. Okay, so hopefully we got this. And even though the spaces are in the wrong spots, hopefully we can translate it to what it was intended to say. Down south with an extra X appended to the end to make an even number of letters. So just a word to the wise here. This is the most complicated encryption we talk about today. And the idea here of, like which one is the row and which one is the column is really easy to mix up because you're going to be going in both the encrypting and decrypting direction. So you got to really take your time. Don't follow the whole process and then realize that you put them in a row when you should have put them in a column or vice versa. So really be sure as you're starting each of these problems in the activities and the homework that you are clear on how you are grouping the numbers when you look them up in the Polybius square.